Hello there, thank you for joining us today for another topic webinar. Today our topic is going to be high throughput soaking condition screening for crystalline sponges, and will be presented by my colleague, Dr. Christian Goeb. But before I hand over to Christian, I just wanted to draw your attention to a few things. So firstly, we have our next topic webinar planned for the 23rd of February. This has not been formally announced yet. This is the first time you'll be hearing about this. If you're interested in joining this, then the registration links will be going live either today or early next week at the latest. And we'll be doing this webinar twice. So once at 10 a.m. in the morning and once at 4 p.m. just to try and cover more time zones. And the topic for that webinar will be on the CrystalLab Synergy ED and how far we've got with the new system in recent times. We are recording this webinar, and the recording will be made available when it's ready. If you want to find it, you'll be able to go to this website here. So this is rigaku.com/webinars past. And if you just go to the webinars page, you'll also be able to get to the past webinars link. And from there, you'll be linked to the recording. During the webinar today, if you have any questions, please use the Q&A function, which should be at the bottom of your screen. In there, you can ask questions and upvote questions by others, and we'll address the questions when we get to the end of today's webinar, which should take approximately 30 minutes or so. Lastly, if you're a customer of ours, then please do join our X-ray forum. It's another place where we'll upload this recording. And there's lots more on there, such as software downloads and help from other customers and past presentations. Okay, with that, I'll hand over to Christian. Christian, if you'd like to share your screen.
Yes, thank you, Fraser, for the introduction. So we can start in a second. Okay, so you should be able to see my screen. Yeah, today I want to tell you a little about how we can utilize our Synergy Flow instrument for high throughput soaking condition screening for the crystalline sponge method. And of course, I want to start with a short introduction. Generally, when you have a new chemical structure that you want to analyze, you have different methods that you can employ, right? So on this graph, we have here plotted structural information versus a decreasing amount of sample that you have for your analysis. And also on the secondary, here we have the state of the sample. It can either be a solid, a liquid, or a gaseous material. So if you have a lot of sample and it's a solid, of course, you are in a very comfortable state because you can do conventional X-ray diffraction. Either it can be single crystal diffraction, so you get your chemical structure out of it here very nicely, or you could also characterize larger amounts in terms of powder diffraction. If your sample is not a solid, but can be dissolved into some solvents, you can still do NMR with two-dimensional spectroscopy. You could determine positions of hydrogen atoms and so on. If you have even less amount of sample, or if it's a gas, then you can still do a mass spectrometry. The isotopic pattern will also tell you at least the elements that are present and the weight of the compound. Yeah, and then the last corner, we can find the crystalline sponge method. As you see, this is a method that could be employed to samples of very little amount. So we are talking about maybe 1 microgram or even to the nanogram regime. This works in a way that you have a solution of your analyte molecule, as you see here, the red dots. You add in a framework type of crystal with some vacancies, and the vacancies can later be occupied with your analyte molecule and then be subjected to single crystal X-ray diffraction. Practically, it looks basically identically to the sketch that I just make up here. You have a tiny HPLC vial in here with a conical shape on the bottom. You load it with a single crystal, some solvent, and your analyte molecule. You let the solvent evaporate, and the analyte molecule of interest goes into the pores. This has already been published, like 2013. There was a nice Nature paper on this. As you know, and Fraser introduced it just before this talk, we have now also an electron diffractometer. Here you can look also into sub-micrometer sized single crystals of your materials. This is just an alternative to the crystalline sponge method. Yes. So the crystalline sponge method in general, you have a linker molecule, this TPT type molecule, and you combine it with a zinc source. Could be either zinc chloride or iodide. Zinc bromide is less often used. Depending on the type of salt you have, different solvent systems that you have, and you synthesize this host structure. The pores of this material, they will be occupied with the solvents from the synthesis. These typically bind very strongly. To make room for your analyte molecule, you have to exchange those to an inert solvent. Typically, hexanes are used, N-hexane or cyclohexane. Could also be longer if you want to have slow evaporation of the solvent, or it can also be smaller, like a pentane, if you want to increase mobility of it. The synthetic procedure is also described in this IUCR journal publication 2016 from Makoto Fujita. There is plenty of good synthetic protocols out there that you can use. The MOF itself, yeah, as I said, it's a porous material. Along the 101 direction, you have pores that are the size of 5 by 8 angstroms. You could include in here analyte molecules that are difficult to crystallize because they are of low availability. They could be gaseous, they could be liquids at room temperature. Because of this type of substance class, this is a very interesting method to work with in aroma industry or in the pharmaceutical industry. Yeah, because this is very interesting for the pharmaceutical industry, we have a collaboration together with Merck. This methodology forward. Rigaku, of course, works on the hardware side, on the X-ray diffraction side. Merck works on the chemical side with the crystalline sponges directly. To show you an example of how this would work, in case you have a gaseous sample, we have here in this sketch the crystalline sponge molecule sitting in a tiny vial. The tiny vial is in a larger vial, and you have some wasabi in here. So the pungent smelly compound of this allyl isothiocyanate can be soaked into the pore. So how would you do this now in practice? You prepare yourself a solution of the zinc source and a solution of your linker source, and a range of test tubes that with screw caps here, of course. And then you layer these. Now on the bottom, you have your ligand solution, and on top, you make a layer of your zinc solution. As you see here, I did a set of different concentrations and amount of zinc chloride salt. You either end up with many tiny crystals or you end up with a few large crystals. So for every setup that you have, the type of X-ray source, the optics that you have, you want to have either larger or smaller crystals. Be aware, smaller crystals soak analyte molecules better than large crystals due to diffusion effects. After you synthesize the crystals in the range that you would like to have, you could at any point stop the crystallization process, of course. You shake down the crystals, collect them in a single vial, and then do a slow solvent exchange. So gradually you need to replace the crystallization liquid with inert hexane or cyclohexane. So after you have done this, now is the time to select the individual crystalline sponge crystals, right? A very good approach is then to pipette individual crystal sponges to this smaller HPLC vials. When you do this, or at this point, you will then add the analyte solution that you have. It could either be, it could for instance, directly come out of your HPLC or from your gas chromatography, add this to the vial, and have then the soaking. Soaking means that you take this crystal in the HPLC vial to an oven, for instance, and you can pierce these GC vials with a needle. This would allow the hexane solution to evaporate and thus increase the concentration of your analyte molecule. The higher the analyte molecule concentration is, the more of this material is forced into the pores, and then because due to the shape of the pores and the interactions you can have with the host framework, these molecules will arrange in a regular fashion, and then you can do the X-ray diffraction on it. Soaking can, of course, be done at elevated temperatures. Here I choose 50 degrees Celsius. This will allow for faster evaporation of the inert solvent. It will also increase the diffusion rate inside of the pores. If you have an analyte molecule that strongly interacts with the host framework, it might even be a good idea to decrease the temperature to fridge, for instance, just to make the diffusion process slower and more mild towards the host crystal itself. The instrument that we used for this experiment is, of course, the XtaLAB Synergy Flow. It is a single crystal diffractometer. It's a cabinet system that includes a robotic sample changer and a dewar. The flow can be integrated to any the seal tube system, the rotating anode system, or our dual wavelengths rotating anode system. Of course, as I said, it has a sample exchanger. Here we have a 6-axis robotic arm. I will also show a little bit later what it comprises of. Here you see the dewar system that we have. It comprises of this drawer type system where you can load in 3 unipacks. This dewar is accessible throughout the measurement. So that means if your instrument has collected data on the dewars, on 2 dewars, for instance, you could exchange them in the middle of the experiment already. There's no need to stop the instrument for a refill. Yeah, and of course, if you have a robot sample changer, you also need a way to automatically center your crystal. So hence we have an automatic goniometer head, as you see it here. Yeah, the universal robot arm comes from Universal Robots, of course. It is mounted to the cabinet in a tight fashion. The position repeatability is plus minus 0.1 millimeters. And when it is not used, of course, it is stored in a way that it would not collide with anything. Yeah, so you have the full scan range. You are not limiting yourself in any way here. Yeah, a word on the end effector. The end effector here works without force and thus reduces the risk of dropping pins inside either of the sample dewar or on the goniometer. On the bottom left, you see how the sample is mounted. Just have a look on the end effector. It's a very new design. On the right-hand side, you see on the upper right-hand corner diffraction image of thaumatin after the first mount and the diffraction pattern after the 10th mount. So you are seeing that there is no icing on the frames. So this is repeatability, and it works very well. So to the sample dewar, as I said, it allows you to load and unload up to 3 unipacks. That means 48 samples. These can be ALS or spine type pins. The dewar can be used with or without liquid nitrogen, and there is a microdosing liquid nitrogen dewar attached to it, so you don't have to think of refilling it. This will be all done automatically for you. The intelligent goniometer head allows to be used with ALS or spine type of sample holders. The crystals can be centered in an automatic way by recognition of the crystal or of the loop. And if you do not want to use it with automatic centering, of course, you can just point and click at the crystal. This is what most of the small molecule crystallographers would do. So this is also usable without the flow system itself. This is the mounting interface that is used with the intelligent goniometer head. Just to show you what the instrument sees when you mount a sample, you see that we use here a Hampton loop. So the blue line means the nylon loop is detected, and the green ellipsoid shows us where is the center of this loop. We also see then, even if the crystal is sitting in oil or in a buffer solution, this is supposed to be a protein crystal, it is recognized. So depending on the size of the crystal, you either want to have the sample aligned on the crystal, let's say the crystal is small versus the loop, or you can say please center it on the middle of the loop when the loop is larger than the crystal. Of course, you have to make a few pre-assumptions. For instance, you give the loop size, the minimum and maximum range, and the aberration of the fiber diameter. Because this crystalline sponge works in cryo conditions, we also have our Rigaku reagents shop where you can purchase all of these cryo equipments that you need. Foam dewars, unipucks, tools, cryo vial clamps, and so on. Of course, for protein crystallography, we also have a few buffer solutions that you can use. Crystallization plates, they can be used also with our crystal check device that would allow you to screen through the individual cells here. It's also very useful in case you want to use it for powder diffraction, for instance. We also have a nice webinar on that. Yeah, so for my experiments, I used the Synergy DW that we have at our demonstration lab in Neu-Isenburg. The DW is a unique dual wavelengths diffractometer. You have a rotating anode with two wavelengths. Rotating anode have a superior flux compared to the microfocus seal tube instruments, and generally you can use it to measure smaller crystals or measure them faster. Yeah, so here just a view onto the goniometer. The rotating anode can be copper or moly or silver. Any two combinations of these wavelengths can be used. The W always comes with a motorized divergence slit controller, so you can cut down the divergence of your X-ray beam. This will allow you to differentiate close reflection spots, either because you have long unit cell axis or because it is twinned. It also helps with crystals that are of higher mosaicity. When you limit the divergence of the X-ray beam, you can resolve also strong mosaic crystals. On the right-hand side, you see here the Hypix ARC 150. This is our largest curve detector, comprises of 3 detector modules. You can also have them as an Hypix 6000 in a flat arrangement or as an ARC 100. So the 100 or 150 is the angular coverage that you have in here. And everything is operated in Chrysalis Pro. So this is a one software suite that allows to operate everything. The XtaLAB Synergy Flow comes with this robotics module. Everything here is integrated and you don't need any external software to queue up your experiment and plan them. So the first step would be that you load your unipucks, of course. And for this, we have a unipuck editor, basically. So you select the individual pins that you have, and you give a sample name, the type of mount that you use. It could be a loop, it could be a mitogen, or like even a glass fiber. And then you choose how do you want this crystal to be centered, on the mount or on the crystal, as I explained it before. Of course, you could also give a comment like your lab journal name, the substance name, and so on and so forth. Barcode refers to, we also have an integrated barcode reader. You will see this in a second. I will show you a short video how this works. You can give the formula of this molecule, and for each individual mount, of course, you could set up different settings. Yeah, you can mix loops of Hampton or mitogens or glass fibers all in one unipack. Is not a problem. So here we see now how this would go, that you interact with the instrument. So I just clicked here on this video to mount and robot interaction. I open the Juva lid now. This will take a few seconds. Then you see that everything is sitting under liquid nitrogen. The Oxford cryostream is at 100 Kelvin already. Let me fast forward this 1 second. So the door has opened, as you see. Now I will insert my unipack that is already pre-cooled, sitting in liquid nitrogen, fill it into the sample Juva, and then close the Juva again, start the action, and the door will close. And this is it for sample loading. Then I want to show you the interface, how you plan a certain robotic task. So you tell just to Crystalline which pins to be selected. So, for instance, I would say, please, of my full pack, pack 1, I want all pins. You see it incorporated the type of mount that I had. And then you just have to choose, do you either want to run this instrument in a small molecule mode or in a protein mode? You can choose which wavelengths you want to use, of course. You could also mix and match between the robotic tasks, of course. Yeah, for the sample screening, you have a detector distance, an offset for the detector, how many frames should be used for the orientation matrix determination, exposure time, and so on. Then, of course, you could dial in certain conditions that you would like to have for the measurement. You could either say, please give me a time constraint data collection, measure anything that is shorter than 1 hour, for instance. For the type of strategy, it can be fully automatic, or you can have a predefined run list, of course. For instance, here we have now a complete data set, redundancy 4, maximum 3 hours. After each individual measurement, you could also say, like, please dismount this, or keep one of the samples mounted. You might have seen it in the previous slide, but now here's a little bigger. On the lower hand side, you see here Crystalline Pro sponge. So this means Crystalline Pro has an integrated crystalline sponge mode. You will put in here just the type of Fujita sponge that you are using, the iodide version, chloride version, or bromine version. Then you could set it up in a way that you want to measure high angle data first. Crystalline sponges degrade slightly throughout the measurement using copper radiation. You want strong radiation, yes, but also because of crystal decay, you might want to measure the high angle data first. If you're using an ARC 150 detector, you have low angle and high angle reflections on the same frame. This helps you with scaling, and thus this setting is not necessary. So you could use a dedicated sponge type strategy for the full measurement. The sponge strategy will look at the scattering intensity at 1 angstrom resolution. So often we find in porous materials that they do not diffract up to 0.8 angstrom resolution, and thus it would give non-meaningful exposure times for the full strategy. Crystal decay can be followed up for the scaling. So this is a B factor refinement that you do, and of course AutoChem is adapted for crystalline sponges. So here you see the auto sponge. We will come to this in a second. So now to the practical terms. We have here our robotic arm sitting already in the sample exchange tuber. It is picking up now a sample in liquid nitrogen. Sample was picked. You will see that here's a barcode reader. So the pins can be labeled with a QR code. The sample is mounted. The robotic arm will now have to warm up this end effector. It will go into this position here. Here is a small heater device that will warm up the robotic arm. In the meanwhile, the measurement starts. I will just increase this overlay window so you see how the sample is centered. The intelligent goniometer head will center on the crystal, right? As you would do, go to 0 degrees, center it, rotate it a bit, 90 degrees, recenter it, and so on. So this is all fully automatic. And yeah, I loaded this whole instrument with 48 samples and have it just cracked through all of the data sets. So lastly, I want to show you the practical part of this talk. I had 3 different analyte molecules. Since I had 3 UniPacs, I wanted to screen them all. So on the left, we see dimethyl dietzein. This is one of the very easy soaking molecules. This is like you could train yourself on this method using this material because it soaks very well. A medium-sized, difficult material to soak is the caffeine. It has these the nitrogen donor moieties. They can be slightly aggressive towards the crystalline sponge network. So this could be an idea to soak at lower temperatures. The success rate might be higher than at elevated temperature. The last one I choose is one of the novel SARS-CoV-2 inhibitor molecules, molnupiravir. This has 3 hydroxy groups, and these amine function here. Acidic protons are normally difficult or demanding on the crystalline sponge network. So we have to see what comes out here. Of course, if you have such moieties, it might be a good idea just to cover them by methylation or something like this. So here's then synthetic chemist is asked. Okay, 3 analyte molecules by using. I used 2 different types of solvent. So dimethyl ethoxide and dichloromethane. In the end, it was a 1 milligram per milliliter solution that was used. 2 different temperatures, 4 degrees and 50 degrees, and 4 types of crystalline sponges. So zinc chloride sitting in cyclohexane and in N-hexane, and zinc iodide sitting in cyclohexane and N-hexane. So in total, this is 16 soaking conditions per analyte and 3 UniPacs times 16 samples. And here are then the results. After you did your diffraction experiment, there is an experiment result viewer in Chrysalis Pro. You can directly look through the individual data sets. So for instance, here we have here pin number 4 out of pack number 3. There is a barcode attached to my pin here. There is unit cell information in here. You see on the bottom, you see completeness of the data set. You have photos of the crystal. You see the scaling plot, the B factor refinement, and so on. So you could quickly look through multiple data sets, sort them. You could even make a ranking score based on, for instance, index reflections or based on RIND or something like this. So you can have them automatically ranked. Since we have AutoChem attached to our instrument in OLEX to refine, we can make like an automatic structure solution and refinement of this crystalline sponges because the connectivity between linker and the zinc moiety is basically always the same. Our AutoSponge algorithm is trained on a large set of solved crystalline sponges, so we can recognize different unit cell parameters, different space groups, and based on these 4 algorithms that you see here on the side, we can do automatic structure solution. BuildNet, for instance, will reconstruct a framework based on the metal halogen units. So you always have these tetrahedral angles around the zinc moieties. The space between is filled with the TPT ligand, and then structure solution stands. Basically, molecular replacement here. Fit ligand, yeah, this is a tool to replace the ligands between the metal halogen units. Substitution, this tool allows to skip the structure solution step and use a database of known sponges to solve the structure. So this is the pure molecular replacement. And AutoSponge will just run all of these scripts consecutively in a row, and it will then take the best structure solution out of it. So once the framework is solved and anisotropically refined, you can directly work on the gas molecule. You will see here, well, you saw that already, that the Q peaks can directly be assigned, and you already see after structure solution, okay, right, there's a dideate inside of the pore. So out of my 3 structure solutions, I try to rank them a bit in a simple fashion, like to very good structure solution, good structure solution. Nothing can be seen in the pore, so here the soaking was not correct, and I was lucky. In one of the flasks, I found pure analyte that crystallized next to my crystalline sponge because it was sitting a bit on the side of the flask. The caffeine, same here. We have some soakings that went well. We have some soakings where we can only see solvent, or nothing can be seen in the pore, and a few crystals just showed powdery features on them. I could not get a structure solution. The molnupiravir, on the other hand, as I said already, like this might have been a little too aggressive on the host framework, and no structure solution could be found. So what do I mean with a very good structure solution? You can see your analyte molecule perfectly fine. You don't need any restraints, not any constraints. It can be freely refined. The ADPs look splendid. Also, you have a space group that is easy to work in. You can have also a good type of soaking where the symmetry of the crystal is broken, and you have to deal with many individual molecules because the soaking was not so uniformly. It's still a good result. You see your analyte molecule, but it's a little more tough on the how to work on it. Yeah, here's the pure analyte. This was crystallized next to the crystalline sponge. This could also be like the ideal case. Yes, this can be centered also automatically, and you get your structure solution from it. Caffeine, I just want to show it to you. This is all freely refined without any restraints. If you have this weaker data, you still see the connectivity, but then it's more difficult to assign carbon, nitrogen, and oxygen in this. Yeah, so this was it for my talk. The high throughput soaking condition screening for crystalline sponges using Synergy Flow. Thank you for your attention, and I'm very happy to answer a few questions if you have any.
Thank you very much, Christian. Nice talk. So we have one question in the Q&A, and if anyone else wants to ask one, please do while we're answering this one. So the question is, can you please elaborate on standard protocol for guest soaking?
So the standard soaking protocol could be that you have your 1 to 2 micrograms of analyte per crystal sponge sitting in 50 microliters of cyclohexane or N-hexane. And from here you can start. I would not go higher with the concentration or amount of analyte. That's not necessary. You can play a little with temperature and with concentration for the soaking and soaking time.
Well, maybe I can ask a follow-up. How do you tell whether your soaking has been successful or not?
You could normally directly see this by visual inspection. So upon a successful soaking, you typically have, to some degree, a discoloration on your crystal. So typically it will go from colorless to like an off-white. And also a good indication that soaking works is that it can go a little bit opaque, yeah, so to speak. So this means that your analyte molecule degrades a bit the crystalline sponge framework, thus interacts strongly with it. This is also a good starting point to lower the temperature and lowering down the diffusion rate of this analyte molecule.
Okay, thank you. How many soaking iterations would you attempt before deciding that the guest cannot be included?
Mm-hmm. So I would normally say for a completely unknown type of material, like 5 to 6 crystalline sponges will be necessary, yes. If you have an idea how your analyte molecule looks in principle, because you have NMR data, you have mass spec data, you could think of modifying that molecule, like I said, like methylation of hydroxy groups or something like this. Yeah. But typically, I would say you need 5 to 6 crystalline sponges for an unknown.
Is there any sort of selective inclusion in the case of mixtures of different guests by using the sponges you have shown?
So the crystalline sponge method works best if you have pure molecules. So typically for unknowns, you would run a chromatography beforehand, because what happens is that you have already solvent molecule in the pores, then the analyte that you want to analyze. And if you then have a third molecule and all are overlaid in your crystal structure, you will not find what you are hunting for. So sample prep is crucial here.
Okay, there are no more questions. Maybe one more follow-up from me. If you're trying to soak something in, based on how it looks or functional groups, is there any way to predict what where to start with your soaking? Like, would you go for, if you see, for instance, lots of alcohol groups, would you go for low temperature or high temperature or something?
Yeah. So the more acidic, the more hydrophobic the molecule, the easier will be the soaking. If you have hydrophilic functions, hydroxy, amines, or ketones or something like this, then you should try a condition where diffusion is lowered. Yeah.
Okay. Okay, well, if there are no more questions, I guess we'll leave it there. So thank you very much, Christian. Very nice topic webinar for us. And I'd just like to remind you one more time that we'll have another one in February. So watch our website and forum for posts on that. So thank you very much, everyone, and have a good weekend.
Thank you, everyone.